Good morning, everybody. Welcome to another session of DSP algorithms and architecture. So, in this first one, we are discussing introduction to DSP, in which we have discussed so many concepts, that is DSP systems, what is meant by sampling process. Then we looked into one of the MATLAB tools on what happens when we do undersampling and oversampling and critical sampling. So these things we had discussed. Then we saw what is meant by discrete time sequences. When you have a continuous time signal, and if you sample it at some sampling rate and you satisfy some criteria, then you'll be able to recover the signal at the other end. Now, if you're sampling the signal at some sampling rate, and you'll be getting only a few of the samples. So those samples are nothing but the sequences what you get. So those sequences are termed as the discrete time sequences. So that is what we had discussed. And if we say sample a periodic signal, we'll be getting a periodic discrete time sequence. So these are things we had discussed. And what is the frequency response? So this equation comes in regularly. This equation comes in regularly. So when we speak of this equation, you can just remember that we are speaking of the frequency response. I think we discussed even these things, that is DFT and FFT. What is meant by DFT pair, and what is N, that is the periodic sequence. Then we just saw that if we have a DFT of a sequence, or if you know the frequency response, how I can get the DFT of that signal from that frequency response using this particular equation. Then we discuss these all things, and what is the analog equivalent of the frequency spacing, that is delta F. So these all things we have discussed in the previous sessions, and apart from this, we discussed what is meant by FFT, and we saw what few of the comparisons related to FFT and DFT. So, and what are the special concepts which come into existence over here. So if we just observe one case, what we can just see is bit reverse addressing. So that is one concept which we can observe here. And we saw how many complex multiplications are required. So along with this, you can also estimate how many complex additions are also required as compared to the direct computation and as compared to the FFT computation. So you can just estimate those things, and you can bring out the differences between FFT and DFT. So now continuing with respect to the previous class. So continuing with the previous discussions, we come across these terms, that is LTI systems, and what is meant by superposition principle in with respect to the systems what we are studying. So these all things we have discussed in signals and systems subject. So let us have a recap of these things. So in this one, we can just see from the name itself, LTI system, that is linear time invariant system. So what it specifies is the system has to be first linear in its response, and then it should be time invariant. So these two things should be satisfied for a system to be called as LTI system. And whenever I speak of LTI system, right, the impulse response, or H of n, what we term in case of discrete sequences, and in case of continuous sequences, it is H of t. So these are the parameters which help us to identify how the system is behaving, whether it is an LTI system or whether it is belonging to some other system. So these all things we can get to know using this impulse response. Now, first thing, what does linear imply? Now, if I have one particular system, I can call that system linear if it satisfies the superposition principle. Now, what is superposition principle? Superposition principle is these two conditions together. That is, if a system satisfies the property of additivity and homogeneity, then I call the system as linear. I call the system as linear. Now here, what is meant by additivity? So additivity is, for example, I have two signals. That is, the system is having two signals, and when I add both these signals, it may be addition or subtraction. So it is invariant in this form. So this is a general representation what we give. Now, if I if I take this system and I try to identify its response, I try to identify what is its overall response. Say, let us call it as HS of n for the system, for which input is x of n and y of n combined, both together combined, and I want to see what is its response. So if h of Sn is its response, then I should get the same response if I take the response with respect to only x of n and add it with the response with only with respect to y of n. That is the two signals in separate. So I can have n number of signals here, and if I am able to obtain, that is using this equation, if I am able to obtain the same response, then I classify it to be additive. I classify the system to be additive. So both should lead to the same responses. Now, if this is not true, if this is not true, so then what happens is I call it as a non-linear system. So if it is non-linear, then actually it is not a LTI system. For LTI, it should be, one condition is it should be linear. So if this condition is not satisfied, then it is not LTI system. So next condition is homogeneity. Homogeneity, what it implies is it relates to the multiplication factor which is involved with the input signal or signals what we are applying. So here homogeneity implies that if input is weighted with some factor and the response is taken, and let me call the overall response as h of n, and this is equivalent to the weighting of the response with respect to the input only. That is, I am weighting the response. Here I am weighting the input signal. Here I am weighting the response with respect to the input signal. So if these two are equal, then I classify it to be homogeneous. I classify it to be homogeneous. In many of the conditions, you might have seen that both the conditions are written together, like in this form. It is generally written in somewhat in this form. So if that is, it includes both additivity and homogeneity. So if this response is equal to A into h of x of n plus B into h of y of n, then I classify the system to be linear. So it is just linearity, the thing what we are looking out for. So the system is classified to be linear if these two conditions are satisfied. If any one of the condition fails, then it is not linear. Then what is meant by time invariant system? So if I just observe here, if input signal is x of n and it produces output y of n, then the weighted signal, that is input signal, also produces a weighted output signal. So if this condition is satisfied, then I classify the system to be time invariant. That is, if I just observe here, see, that is x of n is the input signal and it is producing y of n, the system is producing y of n as the output. Now if input is having some time variance, the same has to result in the output. So that is what we call as time invariant. If all these three conditions are satisfied, then I classify the system to be LTI system. I classify the system to be LTI system. If any one of the property is not satisfied, let it be additivity or homogeneity or time invariance, If these are not satisfied, then it is not an LTI system. So under LTI system, again, it is not only LTI system. We have so many things we come across. So the first thing which we come across is convolution, which we have seen in signals and systems. So it is nothing but it gives us the relation between the input and the output of the LTI system to the unit sample response. That is, it is given by this equation what is mentioned over here, and we can see x of n convolved with h of n, or h of n convolved with x of n. That is, it is uh, invariant to the positions in which you are placing them. So both will end up in the same results. Both will end up in the same results. Sorry, here summation is missed out. So it is again summation is equal to m is equal to minus infinity to infinity. Here also summation should be there. So it will result in the same thing. So this is convolution operator which we represent when we are dealing with signals and systems. So it is basically telling us for a given input, and with respect to its impulse response, what will be the total output, that is the sequence y of n. So it is giving us the input output relation, that is x of n and y of n, with the help of the response of the system. So next one which comes is a Z transform. So I hope you have gone through what is meant by a Z transform. So Z transform is applied to discrete signals. It is applied to discrete signals. So x of n is a discrete signal, and if I pass it through a Z transform, right, I'll be getting another sequence which is in the frequency domain. Which is in the frequency domain. It is x of z, and here generally what we term is z is in the digital domain. Z is in the digital domain. That is how we specify it. And if I have the other, that is, if I have the Z transform of a signal, I'll be able to get back the original sequence with the help of inverse Z transform. Inverse Z transform. Now again, this equation, as I discussed previously, if I know the frequency response of this signal, if I know the frequency response of this signal, and if I substitute e raised to j theta in that equation equal to Z, then I'll be getting this overall equation, which is which will be the Z transform equation. Now this the limits are in the range of minus infinity to infinity. So if you remember, if this is the case for x of n, this is called as bilateral Z transform. And if the limit is from 0 to infinity, it is called as unilateral Z transform. So these are the two things what we have gone through. So if I know the frequency response of a given sequence, then I can obtain the Z transform by just substituting e raised to j theta in this equation. So which turns out to be summation n is equal to minus infinity to infinity x of n into z raised to minus n. So this is the equation which is used to solve the Z transform. Now here if I just see Z is related to the digital frequency what I was speaking, because here this part gives you the analogous equivalent, and the digital equivalent is given with respect to Z. Now another parameter to discuss is the system transfer function of an LTI system. So by definition, the system or the transfer function is defined as the ratio of, say, since we are speaking of discrete, we can define it in the Z transform of the sequences what we have. So we have input and output sequences. So if I want to know what is the transfer function of a given LTI system, then it is nothing but it is obtained by the ratio between the Z transform of the output sequence divided by to the ratio to the Z transform of the input sequence. So which gives us the overall transfer function of the system. Now this is in terms of discrete. Now we also define, we can define these things in terms of say with respect to analog signals, that is in that we make use of Laplace transform. So if I have a signal x of t and output is y of t, for this case, the frequency response can be given with h of s, which is given by y of s divided by x of s. That is, again, it is the ratio of the Laplace transform of the output sequence to the Laplace transform of the input sequence. So here it is Z transform. Here, what is the importance of this system function? So whenever I speak of these things, right, I have a numerator and I have a denominator. Now, whenever I solve this numerator equation, and equate it to 0, I'll be getting some root values. I'll be getting some z values. So the equation will be in terms of z, say z raised to minus 2 plus 1, something in this form. So when I solve this numerator equation equivalent to 2 and I get what are the values of z, so these values gives rise to what is known as zeros. That is, I am equating the numerator to 0. If I equate numerator to 0, I'll be getting some values for z which are called as zeros for the system. And if I equate the denominator to 0, so it is, this gives rise to what is called as poles. If I equate to 0 and obtain the values of z, so these values of z will give me the values of the poles. So these poles and zeros help us to identify what kind of system it is. What is the characteristics of the system, whether it is stable, unstable, what is happening, whether say you might have solved few of the problems identifying whether the poles are lying on the right side, left side, or it is in between. So what is happening, and ROC and other stuffs you had seen in Z transform. So using this, you try to identify it as a right-sided system, left-sided system. If you know the Z transform, yeah, and what happens if it is a right-sided, what happens if it is a left-sided. So these all things you had seen in your signals and systems classes. So this is so this gives us the overall characteristics of the system. Transfer function helps us to identify the overall system, how it is behaving, what is happening. So those all things we'll be able to identify here. So next concept which comes is the digital filters. So these filters, you basically know what they do. Filters, they try to negate the unwanted, say any signal which is present. Unwanted stuff which is present in the signal, they try to remove that. So filters are basically used for that purpose. Suppose, for example, if I'm speaking of a low pass filter, so in a low pass filter, you have to pass only the low frequency signals, and you have to stop all the or you have to attenuate all the high frequency signals. So that is what filter is doing. But in digital filters, we have two different kinds. That is, one is termed as finite impulse response (FIR) filters, and the other one is termed as infinite impulse response, that is IIR filter. So these are the two filters which we will be discussing in this part. First of all, what is meant by filters? Filters basically try to remove the unwanted stuff. And since we are speaking of digital, we'll be using the term as sequence over here. So it tries to remove the unwanted components in the sequence, what you want to say process further. Now they are basically characterized with the help of the impulse response, that is H of n, what we have discussed in the previous case. Now filter, basically when I define filter, right, in technical terms, I can just specify it in this form. That is, it takes the input sequence and generates some output sequence with the help of the impulse response H of n. With the help of the impulse response H of n in this case. So it is trying to operate on those things. Now, how do we represent filters in equation form? So we make use of what is called as difference equation. So if you remember making use of difference equations, we were representing so many stuffs in say DSP and signals and systems. So in these things, we can make use of difference equations since it is a discrete. We are speaking of discrete signals, right? So we have to make use of difference equation in order to represent a filter. So the general equation which comes is in this form, wherein the output sequence y of n is dependent on some coefficients ak and bk, and you can see that these are the previous output. Y of n minus k implies that it is the previous output, and x of n minus k, it represents the previous input, previous output, previous output, and previous input. So depending on what are the coefficient values ak and bk will define your entire system. It will define your entire system. Now here when we speak of these things, right, if ak is 0 for all the coefficients, then what happens? If there is some other stuff, what happens? So that is what we'll be discussing. This is how filters are classified. So if I want to classify the filter as FIR, then these all terms turn out to be 0 and only this will be present. If I want to specify the filter as a IIR, then I have to check in for all this entire equation and identify all the coefficients. Whereas in FIR, I'll be identifying only these coefficients and rest all it will be equated to 0. So these are the filters which help us to identify, that is if we are able to estimate the coefficients AK and BK, then we'll be able to design the filter in an appropriate form. So that is related to this. For DSP, computation time plays a major role. So this is just the representation of the previous equation in its simple form. So this equation is represented over here. So if I just see what I have input x of n and the overall system output is y of n. So these are the coefficients bk what we were speaking, and these are the coefficients related to ak. Now what is happening here is this is the unit delay which delays the signal whatever is given. So here if I just pass it through the first unit delay, it will be delayed by x of n minus 1. So next again if you pass it through another delay unit, it will be x of n minus 2 and so on. So here one thing to remember is so here at the other end what is happening is I want even delayed versions of y of n. So it is y of n minus 1, y of n minus 2 and so on. So it is the representation of this equation. So it is y of n minus 1, y of n minus 2 up to y of n minus y of n minus n. And here if we just observe, it is x of n minus 0, that is x of n minus 1, x of n minus 2, so on up to x of n minus l. So here we are able to represent, that is what is the last sequence we have represented here. It is x of n minus l and here it is y of n minus n. So you'll be getting the delayed versions, and if I able to estimate what should be these coefficients, then you'll be able to design the digital filter. Now again, as I mentioned, you can have direct form 1 representation or direct form 2 representation. So this is direct form 1 representation what is shown over here. Now what happens is, can I reduce these number of adders? So you can see that there are so many adders which are present over here. So can I reduce this number of adders? So this I can achieve in the direct form 2 representation. So but with the increased complex calculations what we have to just look out for. So this is what is the representation of the digital filter. So it is the previous equation what we saw. Okay.